Good morning, everyone. Thank you for the introduction, Rob. My name is Sigrun Karlsdottir. I'm a professor at Mechanical Engineering at the University of Iceland. I'm very happy to be here with you today. I've been enjoying the talks yesterday and looking forward to the others today. My talk today is about high-temperature material testing for corrosion challenges in geothermal environments, and I hope I can give you some insight on the corrosion problems and challenges that we encounter in geothermal power production. So a little background. As we all know, geothermal energy is heat derived within the subsurface of Earth, and the utilization of geothermal energy is dependent on the thermal gradient. Our high-temperature geothermal areas around the world are situated on these geological hotspots, which you can see on the picture to the right, indicated by these red marks. And in these high-temperature geothermal areas, there's a relatively short distance to retrieve energy from the geothermal reservoir. But we also, of course, have lower temperature geothermal areas, and thus we have to drill deeper to get higher temperatures. But the main focus on my talk is about high-temperature geothermal areas. And in our high-temperature geothermal areas, we have high-temperature geothermal wells, basically where we have casings cemented, kind of based on the oil and gas industry designs of wells. And in most of these areas, we produce both electricity and hot water, and that is specifically true in Iceland, where we have 66% of our primary energy on geothermal energy, and 85% of all houses are heated with geothermal energy. And we also like our lagoons. Maybe some of you are familiar with the Blue Lagoon in Iceland, which is actually a man-made phenomenon. It's actually from the wastewater of one of the first geothermal power plants in Iceland. So we have different geothermal power plant designs in utilizing the geothermal energy. Here you can see 3 schematics of different geothermal power plants, courtesy of TWI, which we have been working with on several European projects. And the first one depicted there is the so-called direct steam power plant, where we just take the hot fluid, the geothermal fluid, and that is run straight through the turbine, the steam as it is, and then produce electricity. But then we also have double flash plants, where we also have a lower pressure turbine to utilize to more extent the energy. And then we have these called binary plants, which are also more common for the lower or medium temperature areas, where we actually use a binary fluid to heat up, that we heat up with the geothermal fluid for inlet into the turbine. And then we can have something we call the combined heat and power, and that is exactly where we use also heat exchanger for the condensate from the turbine to heat up hot water that we use for district heating, for example. And then we can have different kinds, like mentioned here. But like I have described, we use the steam straight from the reservoir into the power plant from the high-temperature geothermal wells. So the materials that we used for the power plants are in direct contact with the geothermal fluid, liquid or steam, and thus can be subjected to corrosion. And this is based on, of course, the chemical composition of the geothermal fluid, which is quite aggressive, as well as we have higher temperatures and pressure than known, for example, from the oil and gas. And this is of course, increases the corrosive aggressiveness of the fluid. So hydrogen sulfide and carbon dioxide are gases that are pretty common in geothermal areas and in utilizing geothermal energy. Of course, the temperature plays a major impact in the corrosiveness of the fluids, as well as, of course, the pH level and flow rate. And this can change through from the well throughout the power plant, which I will explain a little bit better later on. So we have different chemistry, different geothermal fluid on these different sites that we have, high temperature geothermal areas. And in this table, I'm basically listing some of the properties of these geothermal fluids and the concentration of the key corrosive species. And we can have, for example, very saline brine from, for example, in the Salton Sea in the US, and high temperatures as well. So we have a very corrosive conditions. So carbon steel casings are subjected to corrosion and are not suitable for that area. Then we can also have a rather benign fluid, such as in some of the areas in Iceland, where we have more neutral fluid or even alkaline fluid, and with not so high chloride concentration, but still CO2 and H2S. So this is just to give you a little overview of how dependent the area and the reservoir location is on what we have for the geothermal fluid and its properties, the properties of fluid. So some of the corrosion challenges that we encounter are, for example, in the geothermal power plants, for example, in gas lines and equipment in the so-called H2S abatement systems. We can also have increased corrosiveness in the turbine components, and that is basically also because when the steam is traveling through the turbine, it is condensing on the later stage, so we have droplet formation, and we can also have some ingress of oxygen if the ejector system is not working correctly. In the heat exchanger, we also have more corrosive conditions because of the condensation of the fluid or of the geothermal fluid steam, and lower pH generated there. And for the high temperature geothermal wells, the corrosion problems are usually when they occur in the casings or the wellhead components. And this can be for some of the acidic wells, such as in Taiwan or Philippines, or for example in some of the areas in Iceland or in the Salton Sea area and the geysers in the US. And this is especially true when we have high enthalpy reservoir fluids or high enthalpy steam, where we can have hydrogen chloride gas also present along with the CO2 and H2S. So of course, in these vapor-dominated geothermal system, where we have very high temperatures, even above 300 degrees, the hydrogen chloride can be present as a from a volcanic origin magmatic gases, and then upon condensation, it becomes extremely corrosive for the carbon steel casings that are often used in these wells. So I want to give you a little intro on what has been going on for these super hot wells that are on the horizon for the geothermal industry and research. The Iceland Deep Drilling Project is a scientific platform that was actually originated 20 years ago in collaboration between the energy companies in Iceland. And the first well that was drilled, the objective was to drill deeper to explore the roots of geothermal systems and obtain supercritical conditions or steam to increase the power output per well. So instead of a 2 megawatt well, we would have a 10 megawatt well. So the first well in this project that was drilled was named IDDP-1. It was situated in the Krafla area in northeast of Iceland. And here to the left, you can actually see when it was first discharged. So this is the wellhead. If a person would be standing, it would be like this high here. It's the muffler. And then we are seeing that the steam is dark colored, it's gray, indicating actually that during the heat up period, we are actually seeing part of the casings here in the steam, corrosion products. After several weeks of flow test, we actually, or the power company, Landsvirkjun, was running the operation and owns the area there. We retrieve superheated steam, and we can actually see that by the steam is clear, and then it condenses when it reacts to the air, and we have this clear white steam. So we had a chance of doing sets of material tests on site in the steam after the superheated steam was retrieved. The wellhead pressure was 140 bars and the temperature 450 degrees. So it was the hottest flowing geothermal well at that moment. We had tests set up for erosion corrosion test, flow loop. We had heat exchanger pipe, long pipes to simulate heat exchangers for testing different corrosion resistant alloys as well as carbon steel material. And we also had the opportunity to put coupons and a specimen holder into one of the legs coming from the wellhead, but the pressure was actually had to be dropped to 12 bar here, and the temperature dropped to 350 degrees. And this is not snow, even though it's in Iceland. This is silica, because also from the geothermal reservoir, we have a lot of dissolved silica, and when we drop the pressure, this is gonna occur. But this was actually surprising how much silica was dissolved. So we were expecting some, but this was quite much more than expected. So we learned a lot from these tests, and we saw that the 304, 316 austenitic stainless steel had cracks and were not good enough for this environment. We also saw, to our surprise, that 254 SMO that has been tested also in situ in different wells had cracks for our heat exchanger experiments, as you can see here, originating from sulfur-rich corrosion products. We have also cracks in the duplex, but overall very low corrosion rate, and we have to bear in mind that this is a superheated dry steam, so maybe not so surprising. After the flow test, actually the well had to be cemented and closed because of corrosion problems in valves. The stem of the wellhead broke, so with further inspection, the carbon steel casings had failed in multiple locations, most likely to thermal cycling of the well, as well as the extreme temperatures and conditions. So the well had to be closed. Our opportunity to explore more was done for our research aspects. So we set up a new project, a PhD project that one of my students at the university did. And we used small reactors simulating super hot geothermal environment based on the chemistry of the IDDP-1 steam. What we did not include was, of course, the silica. So we were testing with H2S, CO2, hydrogen chloride. And this was done in these miniaturized testing facility that we set up at 350 degrees and 10 bars, where we're actually mixing solution and generating the gases inside the reactor. And we did test on these materials that we also had for the on-site testing and had comparable corrosion rate measures. But we did not see as extensive localized corrosion. We saw that for the carbon steel, but not for the corrosion-resistant alloys to an extent. But what's interesting is, for example, the structure of the corrosion layers that formed on the carbon steel, and this has been published in one of our papers here. where we actually seeing sulfur-rich layer forming underneath the magnetite layer, which we commonly see in carbon steel exposed to these H2S CO2 conditions in high temperature geothermal environments. So that was interesting. So we did further studies. Andre set up a series of connected reactors where we actually simulating the discharge, where we have basically wet steam, boiling condition, like we have downhole in the well. We have a superheated state here in the reactor in the middle, and then we have condensation to look at the different stages of the lifetime of these deep superhot wells. And we tested a new titanium grade, the 475, which has a good potential and has been recently developed by TMET, or Special Metals, PCC, and which performed well compared, of course, to the carbon steel, which you can also see from these cross sections here for the boiling state and the condensing fluid. Okay, so this was something to give you an insight on our aspect on super hot geothermal environment research regarding corrosion testing. I want to give you also some insight what we have been doing on corrosion in geothermal systems, not below ground, but above ground for our equipment. And here you see actually a schematic of a power plant, actually a quite complex power plant representing the Hellisheiði geothermal power plant close to Reykjavik in Iceland, close to the capital. And we have, this is the geothermal well, and then we have separators, high pressure and low pressure separators. We have, of course, the turbine unit here, and then we have heat exchanger for a system, cooling towers, and so on and so on. And we can see this is not for Hellisheiði power plant, these corrosion damages, but just showing you for different stages of the power plant that we have different conditions, different pH level for the traveling and drop in pressure and temperature and so on. So different corrosion phenomena or corrosion forms can occur for these materials used for the components. And here we're seeing hydrogen embrittlement effects for acidic wells, which was actually in Krapla area. We have also erosion corrosion effects on our rotors in our turbine units, as well as on last stage. We have the same effect there. We can see a cleaned turbine blade. For our H2S abatement system, we can have also hydrogen embrittlement and cracking, which are evident here in these cross sections and images for typical low carbon steel. And then for our heat exchanger, we have, for example, stress corrosion cracking, particularly if there's 304 or 304 austenitic stainless steel and with chloride does not do well for that environment. So we took part in a project funded by Horizon European Union, Horizon 2020 platform called Geocode, where the objective was to develop a novel and effective corrosion-resistant coatings for high-temperature geothermal applications. And this was done in collaboration with 12 partners, both here in UK, Iceland, Romania, and Norway. And this is courtesy of TWI in Cambridge, where we did actually make quite a lot of different coatings intended for usage of different components in the geothermal power plant to increase the lifetime of the component. And this is, of course, then coated on different substrates to improve the corrosion resistance. And I want to emphasize on these two different types of coating systems, so-called high entropy alloys, multi-component systems, and Cermet's, some of it commercial, other more novel. So in the project that is actually done now, but for the first step in the experimental approach was to do laboratory testing at room temperature. This was, for example, tribological testing, wear testing in our labs, as well as erosion corrosion test at TWI, and electrochemical tests at room temperature at TWI. So the best candidates there were selected from these candidates that I showed you earlier for then corrosion testing in simulated high-temperature geothermal environment, which we did at the University of Iceland. And we set up a new facility with a longer reactor pipe intended to simulate the high-temperature conditions encountered in the geothermal power plant. And the conditions that were selected were pH at room temperature around 4, and with CO2, 1,000 ppm, and H2S, 170. And we, like I said earlier, we actually used solutions that we mixed together and then pumped into the chamber, so we're generating the gases inside the chamber. This is how the setup was for our tests. And what we also did, of course, is to verify by testing some of the state-of-the-art of the material already used in the power plant. And this is a low-alloy steel that has been tested in the flow-through reactor, and it's showing the same kind of corrosion products that we see commonly for these temperatures and compositions. So we are seeing iron sulfide-rich corrosion products with some iron oxide corrosion products in between and underneath. And that is exactly what we see here if we look at the cross-section of the carbon steel or low-alloy steel. These are the samples that were fabricated, having a circular round for fitting into the reactor, as well as having a smooth continuous layer. And we are seeing here this high entropy alloy, cobalt, chromium, nickel, iron, molybdenum coating that has been deposited by laser melting deposition and tested in the flow-through reactor for 7 days. And what we see is actually, if we look at the surface, we can see these globulars, which are actually very molybdenum rich. So there has been some droplet formation instead of complete melting of these particles during the deposition. And we actually saw some sulfur products more evident in these globulars. So our approach was to test it as received with no kind of surface treatment of the coatings before the tests. But we also see chromium and oxygen content increased at the surface, indicating a thin chromium oxide layer forming on the high entropy alloy coating. And if we look at the cross-section, as you can see here, we can see that the layer between, there's a continuous and smooth interface here for the coating and the substrate material. We can see no obvious damages or no obvious damage or cracks or localized corrosion. And so it's a promising results for the high entropy alloy. For the cermet coating, we did detect more nickel sulfide corrosion products at the surface. It also has more porosity. You can see the crystals here forming, being nickel sulfides, as we could see from the elemental analysis. And if we look at the cross-section, actually we saw these cracks, but this is actually most likely from the sample preparation, because these coatings are quite brittle. We can also see some not a perfect layer here between the coating and the substrate. And at the surface, we are seeing some ingress of the sulfur species indicated by these red here colors. So in summary, the high entropy alloy coating of the two most potential coatings for the rotor steel was performing better in our high temperature geothermal simulated environment, and the CERMAT coating had evidence of some ingress and also more porous due to the deposition technique. So the last project that I want to touch upon is our GeoDrill project, which is also a project funded by the Horizon 2020 program. This project is, the objective is to develop a novel and cost-effective drilling technology for geothermal application to advance drilling monitoring through low-cost and robust printed sensors. And of course, to improve component life through advanced materials and coatings, and that is where we come in regarding the temperature, the high temperature testing of the materials. So when we want to drill deeper, and for this drilling technique, the effort is made to try to increase the rate of penetration, and the intent is to drill deeper to obtain higher temperature fluid, for example, in the mainland of Europe, not necessarily in such in high temperature geothermal areas. And this will increase the effects of both wear as well as potential corrosion of the materials. So the approach for this project was, can we develop coatings that can mitigate these conditions? And a set of coatings were produced. This is also in collaboration with TWI at Cambridge, as well as Grafenia in Spain. And there was three main types of coating system developed for different parts of the novel drilling components. The first one was polymer-based with added graphene oxide nanoparticles. The second part was HVOF sprayed, high velocity oxygen fuel sprayed coatings, where we have more conventional CERMATs as well as high entropy alloy coating, previously tested in GeoCoat, and also some ENP coatings or electrolysis nickel plated coatings, which actually have a double layer structure and heat treatment, which we actually had developed from the GeoCoat project. So our findings there kind of fused into this project, and some dry sliding tests, wear tests, tribological tests were done in our laboratories, as well as electrochemical tests. And from that, we down selected the coatings that you can see here for our high temperature corrosion testing. And this is the approach here was to test in our new high temperature, high pressure autoclave corrosion laboratory at the University of Iceland, where we can go up to 450 degrees and 300 bars. And this is a 3-liter autoclave with a gas system, so we can operate and simulate our environment as we choose. And for the GeoDrill project, we wanted to simulate a normal drilling conditions, where we had just tap water, which is alkaline, such as in Iceland. The tap water is used, as well, like the temperature is around 100, 120 we used for this test, and exposed water phase, of course, as I said, tap water, and then we tested for 14 days. For our extreme conditions, that was to resample what can be encountered if you're drilling deeper to these either high temperature areas, or if you're drilling deeper for the medium to low temperature areas. And then the temperature was 250 degrees, 50 bars, and hydrogen sulfide and carbon dioxide gases added. And this was tested for 7 days. And if we have a 50 bar pressure, we actually have two phases. We have a vapor and a liquid phase. So specimens of the same kind were, of course, put in the two different parts in the autoclave. liquid versus vapor. So we had these HVOF coatings, hard coatings tested 120 degrees in water, and they, from the inspection, performed quite well. But for our 250-degree test, where we have CO2 and H2S, damages occurred, corrosion effects were more pronounced, and our cermets were detected with microcracks, as we can see here for the top line. Our nickel alloy flux coating had this kind of two-layer structure, which actually delayed the corrosion effects of the coating itself. And the amorphous coating actually had these voids filled up with corrosion products, so not fulfilling to the standard. But our high entropy alloy coating did quite well, and no obvious effects. We also did the EMP testing of the EMPs and the polymer coatings, and I think I'm kind of run out of time, but we have published a paper on this, so if you're interested, this is tested in the same conditions. And the key factor here is for the 120, we see permeation of the polymer coatings. For the EMPs, they do a little better, but for 100, 250 degrees, these coatings are not equipped to withstand these temperatures, pressures, and the chemical composition with the CO2 and H2S. So of course, acknowledge our partners in these projects and the funding agencies, as well, of course, my group. And none of this would have happened if I don't have these great students and collaborators doing the work. So with that, thank you very much.
Any questions?
You mentioned initially that one of your nickel alloys performed quite well. In the introduction, titanium and nickel alloy 6 to 5. Did you pick that up? Why particularly that nickel alloy performed well, or?
Well, higher grade material, it has, this thin layer, protective layer that formed, so that was, the reason for that. So we didn't see any localized corrosion or any effects.
Because some of your other alloys also, I think, like the hyper-duplex stainless steel there, 254 SMO and so on.
Yeah, but I think for the duplex stainless steels, definitely the temperatures are in the upper part for that. We had, 450 at the wellhead and 350 in the testings conditions. So we were really pushing it for the duplex. So I think that was the reason for the cracking, the micro cracks there.
Any other questions?
Otherwise, I'm happy to also discuss in them.
Maybe I can quickly ask, what's the thickness of the coating? What's the thinnest you can get away with it? Obviously, the thinner it is, the cheaper it will be. I just wonder what. Depending on the coating system. So for example, but for the HVOF coatings, for example, that is, the thickness is like 300 microns, so thick coatings. And the same for the high entropy alloy LC or laser cladded, that was around the same 300, 250, 300 microns thickness. Yeah. Thanks, Sigrun, again.
Okay, thank you.